Good day and welcome to my YouTube class. Today I'm Arthur Francis. It's a pleasure to be with you again. So today we're going to be handling chemistry, empirical and molecular formula. So let's begin with the empirical formula. We say it indicates the simplest ratio in which the various atoms combine. So we're looking at the simplest ratio in which the various atoms combine. So we call that the empirical formula. Let's see, for example, we have Na2CO3. These atoms combine in the ratio of 2:1:3. We have sodium, we have two molecules. We have one molecule of sodium, which is 2 atoms. So in 2, carbon here is 1. So we have our 1, and oxygen here is 3. So they combine in the simplest ratio of that. We also have something like CH4. They combine in the ratio of 1:4. Carbon being 1 and hydrogen being 4. So that is our empirical formula. Then the molecular formula indicates the actual number of atoms of each element present in the compound. Now, in the molecular formula, we also know that molecular formula, by definition, molecular formula is equals to 2 times empirical formula. So this is molecular formula. Aside the fact that it gives us the actual value of the element or compound, it is also 2 times its empirical formula. So to solve questions on empirical and molecular formula, we follow the following steps. So let me read the steps for us. Number 1, write down the percentage of each element. So we're going to write down the percentage of each element as will be given to us. 2, we divide the percentage by mass of each element by its relative atomic mass to obtain the amount of atoms of each element. So we're going to divide that percentage by the atomic mass of each element. If the percentage of carbon is 20, if the percentage of carbon for example is 20, the molecular mass of carbon becomes 12. So we divide it by this. That is what it means. When we solve a lot of the questions that are therein, we're going to see the differences. We divide each amount of atoms by the smallest of the amount obtained to obtain the simplest whole ratio. So when we've gotten our amount in all of the elements that will be present in the compound which we're dealing with, we divide it by the smallest of them all. So whatever we get, now we proceed. Now we express the amount at least 3 significant figures. Very important that our answer should be at least in 3 significant figures. Now, in an attempt to obtain the simplest whole number ratio, do round up proper fractions. Do not round up proper fractions arbitrarily. We should take note of ratios such as this. So now, there are a lot of these things which we're going to solve, you will see. And when we have variables in this form, that we should take note of it. Let me give you a clear example. When we have something like 1:1.5. 1:1.5. So let's say we should not just round it up to be 1:2. This is equivalent to saying 2:1:1.5, which means we'll be having 2:3. So in all the cases, when we solve questions, you will see the differences. In all the cases that we'll have to deal with these, and we have our ratio to be in this form, we should always multiply that with 2. What if we have 1:1.33? For example, we have 1:1.33. Let's say this is the same thing as 3:1, open bracket, 3:1.33. So we multiply this by 3. Here will give us 3, and here will give us something else. So let's see what it will give us. When we use 3 to multiply by that, 3 times 1.33, that will give us 4, the nearest whole number. So when you're having 1:1.33, many a time, the students tend to leave it like this is 1:1 because this cannot be approximated to give you a whole number here. We say it's 1:1. But now we are being told that as soon as we get something like this, multiply it by 3. So this becomes what? 3:4. You will see when we solve questions that will have to be related to this, and you see the difference therein. So we're going to start by taking some questions so that we'll get it clearer. So let's take this. It says calculate the empirical formula of a compound containing 43.4% sodium. Pardon me, let me just carry it. It says it contains sodium is 43.4% of sodium. Carbon is 11.3%, and oxygen is 45.3%. 5.3%. So let's take the question again. They say calculate the empirical formula of a compound containing 43.4% sodium, 11.3% carbon, and 45.3% oxygen. That is it. So let's find out what the empirical formula will be. So first, we say solution. Now we say element given or element present. Element present, we have carbon. Sorry, let's start with sodium. We have sodium, we have carbon, and we have oxygen. Now, percentage composition. Percentage composition. What is the percentage? Sodium is 43.4. Carbon is 11.3. Oxygen is 45.3. Divide by the atomic masses. By atomic masses of each of the elements. So now, the atomic mass of sodium is 23. So we divide this by 43.4 over 23. Carbon is 11.3 over 12. Oxygen is 45.3 over 16. When we do that, we will have 43.4 divided by 23. That gives us 1.89. 1.89. 11.3 divided by 12 gives us 0.942. And this one is 45.3 divided by 16 gives us 2.83. So divide by the smallest here. By the smallest amount. So now, this is 0 point. This is the lowest. 0.942, 0.942, 0.942. When we divide that, we have 1.89, 0.942. That is 2.0. Here is 1.00. And here is 2.83 divided by 0.942 is 3.00. 3.00. So this is the ratio in which they appear. So if that is true, let me now say sodium is 2. So I can now write my sodium here. Sodium is 2. Carbon is 1. Oxygen is 3. So this is sodium tricarbonate 4. This is what it is. So we are looking for what? Our empirical formula. So these are the steps we're going to take. Because of space, I'm trying to be compressing it so that we'll be able to have a reasonable space down. So this is what we have, and this trend we continue to solve other questions. So let's see what we get in the next question. Question number 2 says, find the empirical formula of an oxide of iron containing 70% iron. So we want to find the empirical formula of an oxide that contains 70% of iron. So element given or element present. Let's say an oxide of iron. This is iron. If it is an oxide of iron, it means that there is oxygen therein. Okay? They're giving us 70% of this, so it means there will be oxygen. So we cannot have iron oxide without oxygen. So the percentage composition here will become percentage composition. This becomes, they give us 70%. So the other one will be 100 minus 70 will be 30. Now we divide by the atomic mass which will be, this is 56, this is 16. So when we divide that, what do we have? Let's say iron is 56. All right. So 70 divided by 56. 1.25. We have 1.25. Here we have 30 divided by 16. 1.875. 1.875. Now, having gotten this, we divide by the smallest. Divide by the smallest amount, which is 1.25, 1.25. Here will give me 1, and here will give me 1.875. 875 divided by 1.25 give us 1.5. Remember, when we were solving, when I was reading the rules, they told us that whenever we have anything like 1.5, we should multiply through by 2. So this will be multiplied by 2. Let's put it this way. So here we have 2 times 1 is 2, is to 3. So by so doing, I will have my iron will be 2 and oxygen is 3. Now, let us see if our application of these two, according to the rules they gave us, is reasonable. Before now, we're supposed to have, this is 1:2 approximately. So if I have my iron to be 1 and oxygen is 2, I don't think there is any oxide of iron that is this. But there is an oxide of iron that is this. So you see the reason why we have to follow the rules religiously. Otherwise, we're going to be missing out some essential information. So by so doing, if you have this, it would have been so wrong. But right now, you're correct by multiplying through by 2. And this is what we have. Let's take another question, please. Okay, it's a compound containing 37.1 copper. So let's start with element given first. Element present. Element present. We have copper. contains 37.1 copper, chlorine, and the rest is water of crystallization. Chlorine. And the rest is water. Okay. Now, let us put in the variables. Percentage composition, the next thing. Percentage composition. Copper is 37.1. 37.1. Okay, 37.1. Chlorine is 41.7. 41.7. And the rest is water. So, for us to be able to get the percentage, it's always in 100. And if these two are given, and they say the rest is water, means 100 minus these two will give us that of water. So let us see, we have 37.1 plus 41.7, which is 78.8. 100 minus that, we have 21.2. So here, water would be 21.2. So if that is our percentage composition, we divide by the atomic mass. Okay, just let's divide by atomic mass. Copper is 63.5, 63.5. Chlorine is 35.5, and water is 18. How is water 18? Oxygen is 16 plus hydrogen 2. So we have 18. When we divide that, we're going to have 37.1 divided by 63.5. We have 0.58. 0.58 or 584. Let's take this. Now, 41.7 divided by 35.5. Okay, we have 1.17. 1.17. Then we have 21.2 divided by 18. 1.17. 1.1, approximately 8. So now, having gotten this, the next thing is to divide by the smallest, which is this. 0.584, 0.584, 0.584. Here is 1. And here, 1.17 divided by 0.584 is 2.00. So here is 2.00. And the other one should be almost 2.002. 1.18 divided by 0.584 is 2.02. 2.0. So this means that from here we have copper to be 1, chlorine is 2, dot 2 moles of water. So this is what we have. And so we continue. Now, let's take another one. It's a certain hydrocarbon contains 80% carbon by mass. If its relative molecular mass is 30, determine its molecular formula. Okay, this one has to do with molecular formula. So let's clean the board first. The question is, a certain hydrocarbon contains 80% carbon by mass. So element given, we have carbon, which is 80%. Or let's just call it 80% by mass. And the rest, contain 80% carbon by mass. Now, they're giving us relative molecular mass to be 30, which should determine its molecular formula. Now, hydrocarbon is a compound that contains carbon and hydrogen only. So, if this is carbon, means there is hydrogen there. And that hydrogen is 280 because 80, 100 minus 80 will give us 20. So, this is the percentage. Now, we divide by the, the atomic mass. Here is carbon is 12, hydrogen is 1. So let's go. 80 divided by 12, 6.67. 6.67, and here is 20. We divide by the smallest. Smallest is 6.67. 6.67. Here is 1. And here is 20 divided by 6.67 give us 2.99. So let's call that 3. So this definitely means that carbon is 1 and hydrogen is 3. Remember I told us earlier that the molecular formula, they give us the relative molecular mass to be 30. And I said relative molecular mass is equal to 2 times empirical formula. So yes, so the other way around, we have to look for this. If I have this is given, I can easily say times what to give me the molecular formula. So I don't know what that is. Let's call that n. Is equals to the relative molecular formula here is 30. That is what they give us.